Soil analysis, key to nutrient management planning. This webinar will go through an introduction to the PDA, what is measured through soil analysis, nutrient reserves in the soil, factors affecting soil analysis, effects of different cultivation systems, interpretation of the results, and target indices. The PDA provides information to support correct use of potash in UK agriculture. It does this via the website at pda.org.uk, presentations to groups of students, farmers and advisors, inquiries to the technical helpline, the number for which can be found at the end of this presentation, technical leaflets, which can be ordered in hard copy format from the website or downloaded as a PDF, and quarterly topical newsletters. All of this is provided free of charge. Introduction. Soil provides a reservoir of nutrients required by crops and also therefore for animals, but not necessarily at optimum levels for immediate availability to plants. The purpose of soil analysis is to assess the adequacy, surplus or deficiency of available nutrients for crop growth and to monitor change brought about by farming practices. This information is needed for optimum production. To avoid transferring undesirable levels of some nutrients into the environment and to ensure a suitable nutrient content in crop products. Farm assurance schemes, buyers' protocols and codes of practice are increasingly demanding more accurate fertilizer recommendations, which must depend on the nutrient supplying capacity of the soil. Regular soil analysis every 3 to 5 years should be undertaken as a vital part of good management practice. What is measured? pH, phosphate, potash and magnesium. The standard soil analysis package measures soil acidity, pH, and estimates the plant available concentrations of the major nutrients phosphorus, P, potassium, K, and magnesium, Mg, in the soil. Soil acidity is measured as pH, which is the concentration of hydrogen ions, with a logarithmic scale running from pH 1, being very acidic, through pH 7 at neutral, to pH 14, which is very alkaline. The range found when soil sampling is likely to be between pH 4.5 and 8.5. The total P and K content of a soil can be measured exactly, but has little relevance to crop yield because only a relatively small proportion of the total P and K in the soils is available to the plant. Soil analysis in the laboratory therefore uses chemical extractants to provide an estimate of the nutrient which would be available under field conditions. The results provide the best practical guide for determining P, K and Mg in the readily plant available reserve pool, shown in the next slide. The methods of soil analysis used in the UK have been developed over many years and have been correlated to crop response, and therefore to fertilizer recommendations, on a wide range of soils in numerous field experiments. Other measurements of nutrient content or ratios may be made on soils, but unless there is dependable correlation with yields, they are of limited practical value. Available sodium, Na, can also be measured for potentially responsive crops, such as sugar beet. Nutrient reserves in the soil. The diagram here shows the different pools of nutrient and their relative availability and the relative size within soils. On the left-hand side is the soil solution, where all the transfer of nutrients occur. So applications of fertilizer, manure, and any nutrient provided through rainfall would first enter the soil solution pool. To its right is the readily available nutrient pool. The transfer between these two pools is both directions and is fast. The readily available nutrient pool is slightly larger, and the two of these, including the soil solution, is what is measured by soil analysis. Beyond that is then the slowly available nutrient pool, which is not easily measured. The transfer from here again is in both directions and can be quite slow. Beyond this is the very long-term nutrient and soil minerals, which is not relevant for UK soils. Factors affecting soil analysis. Nutrient values can vary as a result of a number of factors which are discussed in detail here. Further study is needed to define the scale and cause of such variation. Spatial variation. Variation can exist over very short distances, less than 1 meter, and the number of cores that are needed to ensure that sampling is representative of an area will vary according to the scale of this variation. When sampling to obtain an average value for a field, this is not so important, because all the cores taken are bulked into a single sample. For a typically uniform field, 25 cores are sufficient. However, local variation is important when grid sampling, because each grid point is viewed as a separate sample. Normally, because the extent of the variation is unknown, at least 16 cores need to be taken on 1 meter grid spacing around each grid point to provide a single bulk sample for analysis. If it is planned to produce a fully interpolated map of the variability of phosphorus or potassium within the field, then the grid points should ideally be not more than 50 meters apart. However, cost considerations usually limit the number of sample points to 1 per hectare, i.e. 100 meters apart. Where considerable differences occur within a field, a single sample point can be misleading because the averaging will disguise different treatment requirements. If different areas are known to vary, they should be sampled separately. Knowledge of field amalgamations, soil type changes occurred when ploughing or cultivating, visual crop growth differences across the field, or any other specific information on field variation should be used to ensure that the area is sampled to best effect. Alternatively, grid sampling may provide a more detailed picture of in-field variation, albeit at extra cost. Temporal variation. Variations in nutrient values have been observed at different times of the year, and there is evidence to suggest that soil P-K magnesium values may be higher in the early spring than in the autumn as a result of chemical weathering over winter, biological activity, and a lack of uptake by growing crops. Moisture. If soils are dry at the time of sampling, the analytical results can be affected and may appear a little lower for pH, P, and possibly K. Movement and uptake of all nutrients will of course be restricted in very dry soils, but this is a transient problem and does not reflect the normal availability of nutrients in the soil. At present, it is not possible to quantify this effect in order to improve interpretation of analytical results. Crop removal. During periods of rapid growth, crop uptake, especially of potassium, can be large and may deplete available soil nutrient levels for a short period until the nutrient status returns to the equilibrium. This could affect results for some soils if samples are taken at such time. Nutrients are returned to the soil in crop residues, but will not be determined by analysis until the plant material is broken down. It has been suggested that sampling close to harvest may result in an underestimation of true soil nutrient status. Sampling depth. Frequently, there may be a gradient in nutrient levels down the soil profile, usually declining with depth, reflecting the accumulation of nutrients in the plough layer. This is accentuated in minimal cultivation systems, where phosphate and potash may be concentrated in the top 5 to 8 centimeters. With continuous direct drilling, there may be large differences between the top 5 centimeters and 8 to 15 centimeter zones. For permanent pasture, where there is no soil disturbance, a consistent sampling depth of 7.5 centimeters is particularly important. Previous manuring. Applications of fertilizers and manures obviously have a major impact on measurement of soil nutrients. It is difficult to lay down rules as to how soon sampling should be undertaken after application, but general guidelines are 8 weeks after PK magnesium fertilizer application, 12 weeks after slurry or manure application, and 12 months after lime spreading. Ploughing and cultivating helps to distribute nutrients from fertilizers and manures and lime throughout the depth of the cultivation, but this takes time. Effects of different cultivation systems. Regular ploughing, cultivation. Nutrients are mixed into fairly homogeneous soil layer 20 to 25 centimeters deep, depending on plough depth. Nutrient concentrations in a core taken to 15 centimeters should be the same as those in the whole mixed layer. Regular minimum cultivation to 5 centimeters. Applied phosphate and potash will tend to accumulate in the shallow mixed layer, leading to stratification of nutrient concentration in the top of the soil profile. Nutrient concentrations in a sample to 15 centimeter depth will not be equivalent to those in the traditional mixed layer, which is normally to the depth of ploughing. The samples will not be comparable and will tend to overestimate the supply of phosphate and potash available to the crop. Occasional ploughing after several years of minimal cultivation. The soil layer that is mixed by minimum cultivation and relatively rich in nutrients will be buried by ploughing to a depth that is not accessed during normal soil sampling. Samples taken after ploughing can underestimate the supply of phosphate and potash available to the crop in these systems. Interpretation of soil P, K and magnesium. Soil analysis provides an estimate of available P, K and magnesium concentrations in soil to sampling depth. In practice, this is equivalent to plough or cultivation depth because of the distribution of nutrients when the land is worked. Response experiments with different crop groups have provided the relationship between crop yield and soil nutrient concentration. Normally, yields increase with increasing nutrient concentration to a maximum, beyond which there is no further benefit from additional nutrient. Below this value, which will vary with crop species, there is a yield penalty. While soil analysis is not a precise guide, the lower the value, the greater the risk of poor performance. To aid interpretation of the different concentrations of individual nutrients, index or descriptive scales are used. These scales provide a general indication of the likely crop response and therefore a guide to the need for additional nutrient supplementation, as shown in this table. Frequency of sampling. Soil nutrient levels do not alter markedly over short periods of time unless major factors of supply or demand are introduced. There is therefore no point in incurring the additional cost of sampling more frequently than necessary, except perhaps as a check to ensure that earlier sampling has been carried out properly. Additional sampling may be justified where there is a major change to husbandry practice, for instance, alteration of cropping or manure policy. The Farming Rules for Water, which was introduced in April 2018, now states that all soils have to be sampled as a minimum every 5 years. But general guidelines for sampling frequency are as follows. Permanent grass, every 5 years. Intensively used grassland, 3 to 4 years. General arable cropping, 3 to 5 years. Arable grass systems, every 3 to 5 years. And field vegetables and horticulture, every 2 to 3 years. Interpretation of soil pH. The recommended target soil pH values for England, Wales and Northern Ireland, and for Scotland, are shown in the table here, for arable and grassland on mineral and peaty soils. pH values quoted from laboratories throughout the UK are numerically equivalent, even though the extractant is not always water. The Scottish SAC laboratory uses calcium chloride solution, but pH values are converted to be equivalent to those obtained using water. The recommended values in the table are therefore applicable wherever the soil has been analysed. In-field measurements using pH indicator on some soils where free chalk or lime particles exist may give lower values than laboratory results for the same field. This is because grinding the soil for laboratory analysis pulverizes any chalk or lime particles, and the pH as measured is increased. Influence of soil pH on plant nutrient availability. Acidity below pH 6 will reduce the availability of some nutrients, especially phosphorus. Availability of trace elements is radically affected by pH, and the need for trace elements should be assessed only after any required amendments of acidity has been undertaken and has had time to take effect. The availability of different nutrients at the different pH bands is indicated by the width of the white bar. The wider the bar, the more available the nutrient. Principles of P, K and magnesium manuring. The principle of manuring is to maintain plant-available soil nutrient levels within a target range depending upon crop rotation and soil type by replacing nutrients removed at harvest. Soil analysis shows the status of soil nutrients relative to the target values and allows changes as a result of husbandry to be monitored. Where soils are below the target level, nutrient applications should provide more than is removed by the crop to help ensure full yield response and to improve nutrient levels. Nutrient applications for soils above the target range may be reduced or omitted until the soil reserves approaches the target value. Additional nutrients may be applied before very deficiency sensitive crops such as potatoes, with the surplus balance being allowed for in subsequent less sensitive crops. The overall nutrient balance in the rotation should be estimated and then checked by regular soil analysis. Basis of the index system. The target indices shown previously are based on trial work carried out by Rothamsted Research on a number of different crops over a range of differing soil types. The graph shown here shows the yield levels for winter wheat and spring barley grown on soils with varying levels of exchangeable K and the corresponding soil index. As can be seen from the trend line in red, there is no benefit in yield from soils above an index 2. However, below this, the yields start to drop off, and in some cases quite dramatically. Although in some instances yields can be improved on low index soils through applications within the season, the yields do not typically match those grown at the target index where no applications are made. Therefore, maintaining soil P and K levels is key to optimizing yield. Principles of potash recommendations. At the target index, a maintenance dressing should be applied to add back whatever is being removed by the crop growing to maintain soils at the target level. The results from the annual British Survey of Fertiliser Practice indicate that this may sometimes be overlooked, as soils are seen to be sufficient and therefore applications are not necessary. This is an important consideration, as where nutrients are not replenished, soils are likely to slip, which could be more costly, both in terms of yield impact, but also fertiliser applications to build up soil indices, rather than maintaining them at the target. Where soils are below the target, then offtake plus an additional amount should be applied to build soils back up to the target over a number of years. And where soils are above the target, then rates can be reduced from the amounts being taken off, or in some cases omitted altogether, to run the index down, as there is no benefit to having soils that are above the target for the crops growing across the whole rotation. The adjustments built into the fertiliser manual are based on making a change to the index over a 10 to 15 year time period. The rates can be adjusted to make the amendment over a shorter time period, or the PDA's PK calculator can be used to select the number of years. The calculator can be found on the PDA website and is also available to download as an app for both Android and Apple. It should be recognised that potash is unlike most other farm inputs, which are justified on the basis of direct yield response and financial return per pound spent. Correct use of potash to replace crop offtake and maintain soil reserves may not result in an immediate yield response. Failure to replace the potassium removed in the crop and maintain an adequate soil reserve jeopardizes future yields and crop quality and unnecessarily exposes the response to all other inputs. Policies for the lightest textured soils, sands and loamy sands, should be to ensure at least the replacement of removals without the expectation of raising the inherently low levels of soil K to the same value as for other soils. Other factors affecting interpretation. Soil structure. This is also very important because any restriction to root growth may restrict the plant's ability to obtain an adequate nutrient supply despite a satisfactory value indicated by analysis. The remedy is not to apply more nutrient, but to improve the soil structure. Organic matter. The level of organic matter, or humus, will also affect the availability of nutrients in a soil, and regular additions of manures so that the physical conditions and biological activity is improved will increase the plant available nutrient. Stone content. This can also have a large effect on nutrient supply. Very stony soils have little fine earth, yet it is the nutrients in this fine earth fraction that are measured. In consequence, it is advisable to maintain very stony soils at slightly higher levels of available P and K than are required on deep stone-free soils. Soil depth. Crops frequently access some nutrients from below sampling depth and from subsoil, especially potash. Soils with greater rooting depth potential offer a greater soil volume and provide larger total quantities of nutrient than shallow soils. It may be possible to manage deep, well-textured soils at slightly lower concentrations than the stated targets. However, shallow rooting crops, which do not explore the full soil volume, will still require normal nutrient concentrations. Changes in soil nutrient status. Soil analysis measures the average nutrient concentration in depth of soil sampled. Theoretically, a concentration of 1 mg per litre to a depth of 10 centimetres in soil represents 1 kilogram a hectare of elemental nutrient. In practice, however, plants also obtain nutrients from below sampling depth and from the slowly available pool that is not measured by analysis. This often gives rise to some confusion, especially as these sources are very variable depending on soil type and past fertilization and manuring. It is therefore possible to have a soil at 125 milligrams per litre of K, or index 2, which supplies a cereal crop with a peak uptake of 300 kilograms a hectare K2O. Conversely, the addition of 100 kilograms a hectare of phosphorus, potassium or magnesium, and in fertilizer terms this represents 230 kilograms of P2O5, 120 kilograms of K2O and 170 kilograms of MgO, will not result in an increase of 100 milligrams per litre of readily plant available soil pK or magnesium. This is because some of the nutrient applied will not remain in the readily available pool measured by analysis. Unfortunately, the proportion remaining available, and thus affecting soil analysis values, will differ widely with different soils and conditions and is not reliably predictable. With present knowledge, it is not possible to provide more than a very rough guide as to how soil values will change with additions or removals of nutrient. The following figures have been suggested, but it is likely that the range in practice is even wider than indicated. So to increase soil Olsen P by 10 milligrams per litre requires approximately 400 to 600 kilograms a hectare P2O5. To increase plant available soil K by 50 milligrams per litre requires approximately 300 to 500 kilograms a hectare of K2O. More potash will be required on heavier soils where the clay type can make a difference. Potash releasing clays. Some clay soils contain very large reserves of potash, which are not reflected in the level of available K shown by normal analysis. In these cases, the amount of slowly available K released each season may be sufficient to replace some or all of the potash removed in combinable crop rotations, especially where the straw is not removed. The higher demand of root crops and cut grass normally requires some addition. The soil K value may not change over many years cropping, even though little or no potash is used to replace what is removed. Not all heavy soils have this ability, and where less nutrient is applied than is removed, soil levels must be regularly monitored for any reduction in plant available K. So in conclusion, whilst soil analysis is not a perfect tool, it is the most effective and practical means of assessing soil fertility in respect of pH and plant available pK and magnesium. Analytical data should be used in conjunction with other knowledge, such as soil type, structure, and crop offtake, as the basis for deciding on fertilizer and manure use. In an attempt to improve on the reliability of soil analysis alone, there is growing support for in-season monitoring, whether through leaf or sap analysis, and post-harvest grain or forage sampling. The information from each of these steps can help to tailor or tweak recommendations to optimize inputs and improve nutrient use efficiency.